Please, I hope you can hear me. Okay, so today you're going to continue, right? Do you have any questions for me before we start? Okay, then
will you or the TAs be throwing a study session prior to the test, or just the Math Center?
So the idea is, given that we have just 15 minutes and we'll be covering lectures, I have to be teaching. I won't have a lot of time to solve the study session, the study guide questions, right? So what I did was I sent you an email last night talking about all that you need to know going into the exam. I've taken the time to solve each and every question. I try to be as thorough as possible, right? So that one is posted. I have solved everything like step by step, and I've posted it on the Canvas, right? So that should help you out. So the idea is on Tuesday, you have to just you have to use the discussion session for the review. That's the idea. So the TAs will hold the discussion session, but they might not be able to go through all the questions, right? So that's why I posted the solutions as well. And then after that too, you can go to the Math Center. So it's kind of like several ways. So like you have options. So you choose the one which works for you, or combine them.
Yeah, perfect. I got your email. I was just wondering if you were going to do one as well. So perfect. Yeah, thank you.
You are welcome. That's fine. Let me go on. Okay. So yeah, so any other questions? And guys, I encourage you to please try as soon as possible to start solving the questions, right? As soon as possible, right? Try. And if you find any difficult, let me know as soon as possible so that I address them. Okay, so that's all for that. Let's move on to the session if there are no further questions. Okay, so 2.7. I'm sharing my screen. Please, if you can't see, do let me know. So for 2.7.5, we figured out the formula, right? We returned back to the tangent and velocity problems. And we said that right now we know that when you are trying to find the slope of the tangent line, then it's just the limit, right? So we've defined that to be the limit as s approaches a of f of s minus f of a all over s minus a, right? This is the slope of the tangent line at what? At the point a f of a. So we now have a formula, right? But don't forget that the slope of the tangent line is the same as the what? Instantaneous velocity, right? And is the same as, you later realize it's the same as average rate of change. But the entirety of this section is just about a modification of this formula, right? This session is all about this formula, right? A modification. I'll show you what I mean by the modification later on. Okay, so now let's move on. So this is what we found out. And we started solving this and then it was time. So let's try and solve this, right? So now we've now studied how to solve limits, right? So suppose we now have a question. This is the same example that we got when we started the section, right? 2.1. So we have to find the equation of the tangent line to the parabola y equal to s squared at the point PA1, right? Sorry, P11, right? P11. So let's do that on a whiteboard before we look at the solution on the PowerPoint. So I'm sharing the whiteboard now, right? So example 1 on 2.7 slides. Okay, so we have y equal to s squared, right? And then the point is 1, 1. Now we know to find an equation of any line, right? You need two things. You need the slope of the line, and you need the slope of the line, and you need the point on the line, right? So here we have the point and we have the slope. Sorry, we have the point, but we don't have the slope. But we know a formula that we can use to compute the slope, right? So what is the formula? So that's all we need to know, right? So for now, the formula that we have is what? The slope of the tangent line is the limit as s approaches what? A f of x minus f of a all over s minus a. As I said, I'll give you a formula to memorize, but for we'll get a better formula, right? You modify this formula a bit, right? So maybe don't memorize this for now. So this is what you are going to use, right? But then the question is, what is our a and what is our f of a? Now, the a is just the s coordinate of the point that we need the tangent line at. And then the f of a is just the y coordinate, right? And then this function in function notation is just f of x, right? So with this information, right, let's try and compute the slope. So it will just be the limit as s approaches what? The a is 1. And then what is f of x? It's just s squared And then what is f of a? F of a is 1, right? All over x minus a. X is just there, and then a is 1. So we end up with this, right? I mean, the slope of the tangent line is the limit as s approaches 1 of s squared minus 1 over x minus 1, if the limit exists, right? So trying to plug in, let's try and find this limit. Now we've mastered how to obtain limits, right? So we try and first plug in, right? If you put 1 there, you get 1, and then 1 minus 1 is 0. And then if you put 1 down here, you get 1 minus 1, which is also 0, right? So this is a type 0 over 0. So what do? We think about the methods that we learned, the techniques. So the techniques was, okay, if it's type 0 over 0, we kind of try and simplify and then plug in again, right? So with this simplification, what comes to mind is to what? Is to try and factor, right? The expression there, the only simplification you can think of is to factor. Now for the s squared minus 1, this is a difference of squares. So we employ the difference of squares technique. It's just going to be s minus 1, s plus 1, s minus 1, and then all over s minus 1. And then at this point, we can cancel out the s minus 1 terms. So that means that we have the slope equal to what? Limit as s approaches 1 of s plus 1. And then after obtaining this simplified form, we plug in again. So that just be 1 plus 1, which is 2. Right. So now we have the slope of the tangent line to be 2, right? So we have the slope, and then we have what? The point. So we just continue through to find the equation of the tangent line. So the equation of the tangent line is given by, so here you have options, right? You've already talked about these way back in 2.1. So I can use the point slope formula or slope intercept form, right? So I can do y minus y1 equal to ms minus x1, right? So in this case, this will be my x1, this is my y1, and that's my slope. So I'm getting y minus 1 equal to 2x minus 1, right? So that's my final answer. You can end here, or it depends on what Weber-Sein is asking for. If Weber-Sein is asking for like you to write it in like a slope intercept form, then you have to simplify, right? So, but if it's if this occurs in a written part or you're solving, I'll accept this. You don't have to simplify. So just distribute this. You have 2x minus 2 and then plus 1. So you finally get y equal to 2x minus 1, right? So either this or this, right? And that's how you get it. Please, any questions now? So that's how we apply this. So the main idea for this section is we've now developed a formula, right, for the slope of the tangent line, right, in terms of limits. And that's what we have to know. But as I said, don't memorize this. We will see a much more modified formula that we will need to memorize. Please, any questions here? Is there any part you don't understand that you want me to go over? Okay, anybody needs time? Okay, then let's proceed. So let me share. I'm back on the PowerPoint. So this is just going to give us nice notes about what we talked about. So first, we talk about the slope of the tangent line, which is obtained as a limit, right? And then we get this to be equal to 2. And then after getting that, we can just solve for the equation of the tangent line. Okay, so let's look at some other ideas, right? Now, as you see, if we have a tangent line, right? Say you have a tangent line to a curve at a point. Then you notice that at exactly the point of contact, right? If you zoom in, then it turns out that the tangent line and the curve are indistinguishable at the point of contact. They are very, very close. So much so that it's as if the line is on top of the curve, right? Now, this idea is something that we would use when we get to 3.10, yeah, 3.10, right? There will be something we call linearization. So when we get there, you use this idea. But just know that we sometimes refer to the slope of the tangent line to a curve at a point as the slope of the curve at the point. Why? Because at that point of contact, right, very, very close, at that point of contact, the line and the curve are indistinguishable. You see, very, very close in that neighborhood. Yeah, but we use this idea later on. So this is just showing us a graph of what we are saying, right? So if you have the curve like this and the tangent line is on, if you zoom very, very closely, you see that even the curve by itself, if you zoom closely, it looks like a line at that point, at that 1, 1. You see, so the tangent line will be exactly on that curve at that point. Okay, so that's just an idea we explore later on. Okay, so you're just talking about what we talked about. Now, there turns out to be a much, much more simplified formula than what we have, right? So with this one, let me take you to the whiteboard and show you something. So we just established that the slope of the tangent line is given by a limit as s approaches a of f of x minus f of a all over s minus a, right? This is established. We all get this part. But this formula is not always convenient to use, right? Sometimes it could lead to very, very messy factoring stuff. So we have another way of doing this, of writing this, which is the formula that you'll be using, right? So suppose I let h be equal to s minus a. If I let h be equal to s minus a, then, so I'm now going to reconstruct this limit from x to some h, right? So let h equal to s minus a. If h equal to s minus a, then that implies that s equal to what? A plus h. Also, as x approaches a, then h will approach what? Can anyone tell me what is this? As s approaches a, what will h approach? If h is s minus a, then as s approaches a, what is h approaching? Anybody? What do you think? In other words, let me say, what's the limit as s approaches a of h? What is this? Anybody? Okay, now no h, okay, close. At least you tried. That's good. As I said, feel free to speak your mind. Yeah, you were close. So because h is s minus a, think about this. If I write it as limit as s approaches a of h, then it's just limit as s approaches a x minus e. So maybe this one will be much more obvious. So what do you think? What would this be? Perfect, Shane, thank you. Yeah, it's 0, right? Because technically, if you just plug in, it will just be a minus a. So as x approaches a, the h approaches 0. Right? Okay, so that is said. Now, let's try and rewrite this from, we are changing the limit from x to h. So that means that the slope will now become limit, this time, x approaching a. We know that as s approaches a, if you're replacing the s with h, then the h will approach what? 0. And then f of, what is x? We have to change the x from what to something of h. So what do we have x to be? X is equal to a plus h. And then minus f of a. That one is in a. We don't have to change anything. And then what's s minus a? Is h. So you see, that means we now have a formula for what? The slope. Another limit formula for the slope. And this is what you'll be using because this one is more convenient. That's the only reason. Right? Please, are you okay? So this was what I was talking about when I said you have to memorize this one going forward. In the long run, when we get to chapter 2.8, we'll be replacing the a with x, right? And that'll be the ultimate formula you'll be using for the entirety of the session, especially in chapter 3, right? Please, do you have any questions on this? So here, at least learn these two things. We have a new formula now, which you'll be using. This is just more convenient when you're dealing with the factoring stuff. And then the fact that we can sometimes change a limit to a different variable. This will also come up later on. Please, any questions here? Okay, so that's how we got this formula. Anybody needs time here? Okay, then let me go back. So can we stay on this slide? Yeah. Donovan, let me. Yeah, so I'm here. Please do let me know when you're done. Yeah. Maybe let me say more convenient to use. Oh, good. Perfect. Okay, so let me go back to the PowerPoint. Okay, so that's where you're getting this from, right? So here it just says that when we let h equal to x minus a, then we can express the slope of the secant line as this, right? As f of a plus h minus f of a all of h, right? So in that case, we've changed it from x to some a plus h, right? Because if you let h equal to s minus a, then x is equal to a plus h. So how does this make sense? Well, this makes sense in a case that we've just decomposed x into what? A plus h. And then we are letting the h approach 0. Because think about this. If initially you had a point A and you are approaching it like the x was approaching the A, and then now you've transformed. So see, at first you had A, right? And then you're letting the s approach the A, right? So that was the limit. So now if you let the h be equal to the s minus A, that means that the x is now a plus h. So the x that was approaching is now in the form a plus h, and then the h is varying, right? So if you're letting that thing approach the a, then that means that we need the h to be as small as possible for it to be close to a. You see, that's how this makes sense. And that's the diagram that you see here. So it's just the same formula. It's just justifying the formula, right? So this time we are letting this h vary. And if in order to get it close to the a, you need the h to get close to 0. You see? Yeah, so that's this formula. Please, any questions here? Okay. Now, so this is the formula that you'll be using. So this is the expression. It's more convenient, right? The one that we just developed. So the slope of the tangent line, and as you see, the instantaneous velocity equal to what? The limit as h approaches 0 of f of s minus f of a plus h minus f of a all over h, right? Yeah. Okay, and that's it. Please, any questions here? Anybody needs time? Okay, then now let's move on. So now that we know the formula, right? As I said, for all that we are learning here, it's just that formula. So this is a formula I was talking about. It's just this. It's all about this formula, right? For the 2.7, the summary is all about this formula, right? We know that this formula represents the slope of the tangent line. This same formula represents the what? Instantaneous velocity when the f is not a curve, but rather a position function, and so on and so forth, right? It's all about this formula. Okay, so now let's deal with this. This one says find an equation of the tangent line to the hyperbola y equal to 3 over x at the point 3, 3,1. So let's try this. So this is example 2. Example 2 on slides. Now, one comment. For this special limit that we have, right? This is a special limit, right? It's a special limit. For this special limit that we have, you notice that whenever you plug in, it will always end up with type 0 over 0. So you don't need, when you are finding this limit, you don't need even to think about what you are going to get. Don't even try by plugging, start by plugging in. Just go straight away to try and simplify and cancel out common factors and plug in again. You see, because if the h is 0, if you plug it in here, you get f of a minus f of a all over 0. And f of a minus f of a is 0 over the 0. So you always get type 0 over 0. So don't even start by plugging in to check. You can just jump that step and then just go straight toward trying to simplify, canceling out common factors or something, or rationalizing, right, to get your answer. Okay, so now let's go. So for this one, we have y equal to 3 over x. And then the point is 3,1. We need a tangent line here. So what do we do? So to get a tangent line, we need to get what? The slope, which we have a formula for. It's now limit as h approaches 0 of f of a plus h minus f of a all over h. And please, you need to memorize this formula going into the exam. I mean, the one with the X, the X replaced, the A replaced with X, which will be in chapter 2.8. But it's not too different from this, right? So please note this formula. You need it on the exam. So when a question asks you using the definition of a derivative, this is the formula you have to use. You can't use the rules. If you use the rules, then it's zero, right? You can't use the rules because you've not learned that yet. Okay, so that's just a side note. Now let's go. So for this one, what is our A? You know our A is the S coordinate. So this is our A. A is 3. And then the F of A is the Y coordinate. So that's 1, right? So let's just fit everything together and see where we are at. So that means the slope is the limit as H approaches 0 of F of what is A? So A is 3, right? So you have 3 plus H minus F of what? A. And F of A is 1, is the Y coordinate here. Maybe let me just put this there. Or maybe let me write this before F of 3. No, not F of 1. So this F of 3 all over H. So that's the slope, right? Okay, so now moving on, what is F of 3? F of 3 plus H. That would just be 3 over, don't forget that in function notation, Y equal to 3 over X is the same as F of X, right? I think this will be a better representation to see. So for the F of 3 plus H, that would just be what? Plug in the 3 plus H for X, and that would be the same as 3 over 3 plus H. Right, so we have 3 over 3 plus H. And then minus for the F of 3, we just have 3 over 3, and then all over H. Please, are you okay up to this point? Any questions? Anybody needs time here? Okay. So then moving on, let's try and get this. So we get M equal to what? The limit as H approaches 0 of what? So for this one, we have a complex fraction. So what do? We find an LCD, right? So let me perhaps write the LCD here before I proceed. So LCD would just be 3. Okay, this 3 goes to 1. So 1 and 1. So LCD is just 3 plus H. 3 plus H. Right. So what do we get? We are getting something like 3 plus H, which is the LCD, times 3 over 3 plus H minus 1. Right? This 3 goes into 3, that's 1. Then all over 3 plus H and then H. Right? So we get the slope to be equal to the limit as H approaches 0. And then we distribute the 3 plus H, right? Don't forget that by multiplying the numerator and the denominator by the LCD, I don't change the expression, right? So, and I'm using the LCD so that I can reduce everything to a much more simplified form. So the 3 plus 8 distributed, that will go through. So we get 3 for the first part. Then 3 plus 8, that's minus 3 plus H. And then all over H times 3 plus H. And then we get the slope to be equal to limit as H approaches 0. Then 3 minus 3, that'll go away. So I have minus H over H, 3 plus H. And then the H's will cancel. So I have slope equal to limit as H approaches 0, negative 1 over 3 plus H. Right. So at this point, what do? We just try plugging in again. So that means we get a slope to be equal to negative 1 over 3 plus 0. So the slope equal to negative 1 over 3. Please, are you okay with this? Yeah, so we have the slope now. Oh, wait. How did you get the 3? Oh, okay, on the last slide. Okay, so good question. Let me go back to how did I get this term, right? Okay, so let me do this, right? I think this place is already full. Let me go back. So we know f of x. So this is just a side note. Let me put this. We know this is 3 over x, right? And then in the formula, we know we have to do f of 3 plus h, right? F of 3 plus h. So if you have f of x to be 3 over x and you are looking for f of 3 plus h, what are you doing? You're just plugging the 3 plus h for x. So wherever you see x on the right-hand side, you put in 3 plus h. So that's why we have 3 over 3 plus h. Please, I hope it makes sense now. Are you good? Are you okay on that? Got it. Let me go there. Okay, you got it. Okay. Do you want me to? You got it. Okay, nice, nice. For this previous slide. Okay, you got everything? Okay, okay, okay. Okay, cool. You're welcome. You're welcome. Fine. Okay, so then let's proceed. Any other questions? Oh, but we are not done. I should perhaps not like put this in a rectangle yet. We are not done. So now we have the slope to be -1 over 3, and you have the point. No, let me change to black. You have the slope to be -1 over 3, and we have the point to be 3,1. So we can now find the equation of the tangent line, right? But I'll need to move on to the next slide. Do let me know if you need time. Okay. So that means that we have slope -1 over 3, and then the point is 3,1. So the equation of the tangent line, what is 3 adding? Wait, so let me see, guys. Okay. What is 3 adding to the top on the last slide? 3 adding to the top. 3 adding to the top. Looks like an 8, but I couldn't tell. Which one? Oh, wait. Oh, sorry. Yeah, that's true. So 0. The 0, it overlapped. I'm plugging the 0 for h. You see? Yeah. Okay. You're welcome. Okay, so now let's go. So that means you have y minus y1, which is 1, equal to the slope, and then s minus 3. So you can end here, or you can solve further, right? So that's just -1 over 3x. And then -1 over 3 times this will be +1. And then we have +1 again. So you have y equal to -1 over 3x plus 2. So that's your answer. All right, so either this or this. Please, are we clear on this? Any questions? Okay. Anybody needs time here? Okay. Then let me switch to the PowerPoint. Oh, okay, I left space. So check whiteboard for solution. Okay, so now let's go. Now, as I told you earlier on, this same formula comes about when you're dealing with velocities. As I told you in 2.1, the velocity problem and the tangent problem are not different, right? It's just the function, the f, the name of the function has changed, right? It's no longer called the equation, the function, right? It's not like a function of a curve. That function is now called a position function. And then we are no more looking for the slope of the tangent line. We are looking for instantaneous velocity. So it's the same thing that happens, right? You have to get that. If you get that part, then you know that this session is all about one formula, right? But the function name can change, right? So with the velocity problem too, suppose we have a function which is the position function s, right? And then the s is given in terms of time, right? So we have a function of t, right? F of t. So s is the displacement, right? Directed distance of the object from the origin at time t. And then the function f that describes the motion is called position function, right? So for position function, what do we do for the velocity problem? If we want to find instantaneous velocity, we have to use the limiting value of the average velocities. And average velocity is change in position, which is this, right? So between the time interval a to a plus h, the average velocity is change in position, which is f of a plus h minus f of a over change in time, right? So over time displaced, right? The t is a and then a plus h. So if you look at the change in time, right, then that will just be a plus h minus a, which is h, right? but through it all, you get the average velocity formula to be the same as this, which is the same as the slope of secant line formula you found. As I said, it's not the different ideas. It's the same thing. It's just that the function name has changed. It's no longer called the equation of a curve. This time it's called what? A position function. That's all there is, right? And then that's all there is to this. It's the same limit you get, right? So if you look at this one too, if you grab the position function and then you let the a plus h approach the a, where the h is varying, then that means that the h is approaching 0, right? For the tangent here, right? Which will give us the slope of the tangent line here is the what? Is the instantaneous velocity, right? So it's the same thing. That's what I'm saying. It's the same thing. So you get the velocity to be equal to what? The limit as h approaches 0, f of a plus h minus f of a all over h. And this is the instantaneous velocity at time a, right? As I said, it's the same formula, right? I mean, that's why we got the name, the derivative from, because that same limit occurs in several different function forms. Right? If it's called a position function, that limit is called instantaneous velocity. If the f is just an equation of a curve, that limit is called what? The slope of a tangent line, and so on and so forth, right? So the same formula occurs here, right? Please, any questions here? Okay. So it's the same idea as I said, don't think too much about this, right? It's the same thing, just that the name of the f changes, but same limit, right? So let's look at example 3. So suppose that a ball is dropped from the upper observation deck of the CN tower, 450 meters above the ground. What is the velocity of the ball after 5 seconds? And B, how fast is the ball traveling when it hits the ground, right? So for this one, I'll need a velocity, I'll need the instantaneous velocity formula for these two calculations. So instead of finding the velocity at time 5, I'll find it for a general time, right? Because I'll use it here and then here. So let's do this together. Did I leave space for this? Oh, the solution is here. So let me just do this on the whiteboard. So we have example 3 on slides. So we know that the instantaneous velocity at A, right? Instantaneous velocity at time A, right? This is given by the same limit as h approaches 0, f of a plus h minus f of a all about h is this formula, right? So in this case, we are told that the ball falls from upper observation deck. From 2.1, we learn about Galileo's law, right? We say Galileo's law is, if I'm 4.9 t squared. Yeah, I think that's it, right? It's 4.9 t squared. That's the position function. It's 4.9 t squared. You can call this f of t or s of t. Yeah, that's the position. Maybe let me just call it. Yeah, that's fine, f of t, right? So let me erase this. So the position function s is equal to f of t, right? 4.9 t squared. So if you want the instantaneous velocity at any time, right? As I said, because this question has 2 parts, I won't do at a specific a, right? So I won't do, say, at 5. I need the instantaneous velocity at time 5, but I need the velocity formula for the second part. So I'm doing it for a general a, and then I can use whatever a I need the instantaneous velocity at, right? So let's find the instantaneous velocity at a general a. So for this problem, we need to figure out f of a plus h. What is that? That's just going to be what? 4.9, right? If you put the a plus h in place of the t, it's just 4.9 what? A plus h squared, right? So let me simplify this a bit. I get 4.9, and then for this one, I can factor this. You can use the FOIL, or you can use the perfect square binomial shortcut, right? The square of a binomial. So you just square the first term plus 2 times the product of the 2 terms. So that's a times h plus square the last term. So that's h squared. Wait. Let me see. That's 4.9 a squared plus 2ah plus a squared. All right, so we are here. Please, any questions here? Anybody needs time here? Okay, so now let's follow through and find the other parts. Now this one, I must say that 2.7 and 2.8 using the formula is something that no one likes to do. That's why you appreciate chapter 3 more when we get there. But we have to make do with this in the chapter 2. That's why I said the rules are not allowed. Using the rules is equivalent to like you're cheating ahead of us. So yeah, the rules are not allowed for 2.1 for the first part. So now let's do this. So for f of a, what is f of a? We already found f of a plus h, right? So let me write the f of a plus h. Let me distribute the 4.9. So that'll be 4.9 a squared. I'm stretching my 9 so that it doesn't coincide. And then this one, 4.9 times 2ah, that'll be, that's 9.8, right? 2 times 49, that's 98, yeah. So 9.8 ah, 9.8 ah, and then plus what? Then the last term is 4.9 a squared. So let me probably erase this. 4.9 h squared, right? So what is f of a now? For f of a, looking at the formula, it's just going to be f of t is 4.9 t squared. So f of a is what? 4.9 a squared. So that's 4.9 a squared. So that means your f of a plus h minus f of a. I'm just trying to make my life easier. I don't want to write a very long like factor when I'm using the formula on the top. So I'm just doing for the top here, f of a plus h minus f of a. When I'm done, I'll put everything together, right? So that means this one is just going to be the top one minus the bottom, right? So the 4.9 a squared, these two will cancel out, right? And then what will be left is what? 9.8 ah plus 4.9 h squared, right? So now I have the top, my life is a little bit easier. So I can find the instantaneous velocity at any time a, right? So that's the limit as h approaches 0. F of a plus h minus f of a, that's this, right? So that's 9.8 ah plus 4.9 h squared, and then all over what? H. So if you are trying to find this limit, as I said, you always end up with type 0 over 0. So don't even bother plugging in, right? So just go straight to the simplification part. So here I see a factor of h and h. So I can factor that out and I have 9.8 a plus, and then 4.9 h all over h. At this point, the h's will cancel out. And then that will leave me with the instantaneous velocity given by the limit as h approaches 0 of what? 9.8 a plus 4.9 h. Please, are you okay with this? Any questions up to this point? Okay, so simplification is now complete. So what do? I try plugging in again. And don't forget, you are taking the limit as h approaches 0. How did I cancel? Okay, so I mean, I'm thinking you mean this step, right? The 4.9. Yeah, so I factored out an h. So I have h here and then h here. You see, I have h here. So I factored that out. So that'll leave me with h times what? 9.8a plus 4.9h. And then all over h. But then I have common factors here. I have h and h here. So that's how I canceled out. Please, are you okay with this? The step before. Oh, this one, the 4.9 a squared, you mean? This one. Is it this? Oh, yeah. So I'm doing f of a minus f of h. So it's this top here minus this down here, right? So 4.9 a squared minus 4.9 a squared, they will cancel out. You see, that's how I got it. I hope it makes sense now. Okay, you're welcome. So at this point, as I was saying, you plug the 0 for h. So you're getting 9.8a plus what? 4.9 times 0. So that's what? 9.8a. That means the instantaneous velocity at any time a is just given by this. So now let's go back to the question, right? So let's go back. The question was asking about the velocity at what? Time 5. So instantaneous velocity at time 5. So I just need to plug the 5 in place of a. and then I'll get the instantaneous velocity at time 5. So that's question A. So question A, instantaneous velocity at time 5. That will be given by V of what, 5. So that's just 9.8 times 5. And that's equal to what? 49 meters per second. Please, are you okay on this? Okay, so I have my answer now. So that's for A. Anybody needs time here? Okay. Okay, all good. Okay. I see a question. If we get another problem, the ball falling, can we just assume 9.8? No. Please don't assume this, right? The formula that I gave you, the formula I used here, is because it's a law of falling bodies. But in a question, we will give you the position function for sure. The position function will be given to you. I won't assume that you memorize the 4.9 t squared. No, right? I won't assume you memorize this. I'll give you the formula that you need to use. Okay. So if you're good now, let me go back to the PowerPoint. Now the part B says, how fast is the ball traveling when it hits the ground, right? So this one is asking about instantaneous velocity at the time it hits the ground. Now don't forget that you are standing on top of a tower, right? And you're dropping the ball, right? So at the time that, at the point where you started, when at the starting point, the position is 0. Now we know that the tower is 40 meters above the ground. That means that for the time that it hits the ground, its position is what? It's 450, right? Because it's 40 meters above the ground, right? So that means that we need to first find the time at which we hit the ground using the position function. And then we find the what? How fast, which will be the instantaneous velocity at that time. All right, so that's part B. So for part B, I know the position function, which is the f of t, is 4.9 t squared, right? So when it hits the ground, the position function equal to 450, right? So that means this is what, 4.9 t squared. So let's solve for the time. So that'd be t squared equal to 450 over 4.9. And you're looking at a positive time. So that'll just be the positive square root of what? 450 over 4.9, which will give us approximately, I'm thinking 9.6 seconds, but I'll verify from the slide. Let me see. 4.9, yeah, 9.6 seconds, yeah, that's true. Okay, so 9.6 seconds. So now that we have the time, if you want the velocity, instantaneous velocity at time 5, at that time, so not at time 5, at that time, right, which is the 9.6 seconds, then that means you're just trying to find the V of what, that time. So let me not use the approximation, let me use the actual value. So that just be equal to what? The 9. What's the formula for the instantaneous velocity? We got the formula back here. It's 9.8 times what, the A, right? So that just be 9.8 times this thing, right? Or 9.8 times 9.6 if you want to approximate, right? So that's 450 over 4.9. So that would be approximately, I think 90 something, but let me check. Yeah, 94 meters per second. Is it 94 meters? Yeah, 94 meters per second. And that's how you get it. Please, any questions here? So there's the speed, right? Sorry, there's the velocity at when it hits the ground. That's how fast it's falling when it hits the ground. Please, any questions here? Anybody needs time, more time here? All right, so that's how you do it. And this is an application question. Okay. A question on the exam. No, this is just an application, as I said. This is if you get a question about the velocity and position function, it will be in the homework. I won't ask you an acceleration question on an exam, but I can ask you to use the definition of a derivative for sure, right? Because in the study guide, you see problems like that. Okay, anybody needs time? Did I see? I don't know what I was waiting for someone. Okay, no one. Okay, I think, are you guys done? Please communicate if there is anything, right? If anything comes out, let me know. I won't be able to tell what is happening at your end unless you let me know. Okay, so I assume you are okay. Okay, then let me just go back to sharing. Okay, so this is just nice notes, right? On the PowerPoint. So what's the velocity? So as I said, for this one, we found the general velocity, right, at any time, because you are going to use the instantaneous velocity here, and we also calculating there. If you do it for only v of 5, then when you get to the second part, you have to do v of whatever answer that we got, the 9.6 seconds thing. You see, the 9.6. So in order not to do it twice, we found it for the general. So this time, they didn't use A, they used T, right? But it's not different. It's just that we have to acknowledge that the time is the A, the T is the A, right? So using the formula, they did it straightforward, right? So we are looking at limit as h approaches 0, and f of what? They use t plus h minus f of t all over h, right? So t for time. And then the formula is what? 4.9 t squared, right? As I said, we'll give you this formula. You don't have to memorize any of these formulas. So then that's, I mean, for the position function, but you have to memorize this standard rule for getting the derivative. Okay, so we get limit as h approaches 0, 4.9 t plus h all squared, and then this, right? So you put the t plus h in place of the t, right? So that gave us this. We solve this, we get this, and then after everything, we get 9.8. In our case, we got 9.8a, right? So in that case, that's velocity at a. It's just the a that's changing, right? But here they call it v of t, right? So if you want the velocity at time 5, you just put in 5. Instantaneous velocity at time 5, you just put in 5. Right? So that gave us 49 meters per second, right? And then for when, since it's 450 meters above the ground, when it hits the ground, the position is what? 450. So we can use that to solve for the time, which was approximately 9.6 seconds. And then we are looking for how fast it's falling, right? So we need the instantaneous velocity at that time. And that's this, which is approximately 94 meters per second. Please, are you okay with this? Okay, so they're just nice notes. Now, let's move on to derivatives. So as you know, we said that the instantaneous velocity and then the slope of the tangent line are all using the same limit. And that special limit is what you call a derivative, right? So this one is saying the same type of limit occurs, right? So this limit of this form arises whenever you are calculating a rate of change in any of the sciences. So for any field that you're working in, if you're looking for a rate of change, then it's just the name of the function will change, but this limit always comes up if you're looking for a rate of change, right? So it has a special name, right? Because it's widespread, it has a special name and notation. So let's look at this special name. We already saw the special name. The special name is called the derivative, right? So the derivative of a function, f, at a number a, is denoted by what? F prime. So in order not to be writing m when we are looking at the slope of the tangent line, and maybe write v of a when you're looking at the instantaneous velocity, they developed one single notation for all of that, right? So one single notation is going to take care of every kind, whether it's m, v of a, or whatever, right? As long as it's a rate of change, they do f. This one is read f prime of a. That's how we read it. So it's f prime of a. So this one, as I said, f prime of a. So from now onwards, whenever you see f prime of a, it means the slope of the tangent line. It means what? The instantaneous velocity at a, and so on and so forth. It means the rate of change of the function at A, right? So what is the formula, right? The formula is the limit as h approaches 0 of f of A plus h minus f of A all over h, right? And as I said, don't forget that we can also say that the f prime of A equal to what? The limit as s approaches A of f of s minus f of A. After all, this is what we started with, and then we got here. But this is more convenient. This is what we have to use from now onwards, right? So that's the definition of the derivative. Please, any questions here? I understand it's 11:15. So let me. Okay, yeah. So you end here, right? Yeah, we end here and continue on Monday. Yeah, but please start solving the study guide problems. Let me know if you have any difficulty. You can schedule an appointment if you want to work some questions with me. I think your TAs are also there for you, right? On Tuesday, you'll be doing study guide, like you'll be preparing for the exam, right? So that's all for today. Thank you for your time.
Thank you.
You're welcome.
Thank you.
You're welcome.
Thank you.
You are welcome. Yeah.
Is the study guide on Canvas in some spot?
Yeah. So it's on Canvas. It's in a folder, which is I think exam 1 study guide and solutions. That's how I named it. Yeah. So you get the solutions and the questions. Yeah.
Is it in files or pages?
I think it's in files. Yeah, files. So go to files, and then you see the exam 1 study guide and solutions. When you click on it, you see the solutions as well as the study guide.
Okay.
Yeah.
Thank you.
You're welcome.
Have a good day.
Same to you. All the best.
Thank you so much, Professor. Have a good weekend.
Same to you, Hunter. You're welcome.